It is 6:30. It is fantastic to see such a great group of people here, to the extent where we've had to bring in more chairs. That is a relatively uncommon occurrence, so really pleased to see you all here. For those of you who don't know me, my name is Sandra Kentish and I'm Chair of the Victorian Division. Let me start by acknowledging the traditional owners of the land on which we meet, which is the Wurundjeri people of the Kulin Nation, and pay respects to their elders past, present and emerging. But I'm delighted today to introduce a fantastic seminar on battery technologies. I'm going to introduce our chair for the evening, who is Doug McFarlane. Doug is a Sir John Monash Distinguished Professor at Monash University. He has degrees from Victoria University of Wellington, Purdue University, and now works at Monash. His interests include electrochemistry applications. You'll hear more about that. He's published more than 800 papers. That's pretty impressive, with an H index of 134 and a highly cited author since 2019. He is, of course, an ATSE fellow, as well as being a fellow of the Australian Academy of Science. I could go on, but I will pass over to Doug to kick things off. Thank you.
Thank you, Sandra. And do we have some online participants tonight? Two. Okay.
There's 5, it says up there now. Well, one of these ones.
There we go. All right. So it's going to be important talking to the speakers here that we use the mics, right? Because personally, I'm inclined to wander off, but not tonight. Okay, so my job here is to convene and moderate, if necessary, the discussion. We're mainly here to have hopefully a good discussion, share our views on what the future might look like in this area of batteries and energy materials. And we'll lead off with relatively short presentations before discussion time with our two lead speakers. So let me first of all then please introduce Bruce Godfrey, Dr. Bruce Godfrey, member of the Academy. Bruce, perhaps his current activity that's most relevant tonight is that he is the non-executive director of the Future Batteries CRC, which has been running now for quite a few years, Bruce, hasn't it? 4.5 years, right? So that's a key focal point in the country in terms of battery developments, right? And other things that he does includes he's a member of the Charles Sturt University Council. He's a member of the Australian Renewable Energy Agency Advisory Board. And not written here, but very important, I want to add that he's also a member of the Scientific Advisory Board of our spin-out company, Jupiter Ionics, just slipping that in there. So that said, please welcome Bruce.
Thanks, Doug, and thank you all for coming to listen to Amanda and me, and hopefully we will be able to answer a bunch of questions that you might have later on about this fascinating industry called, well, I call it advanced batteries, and particularly in this case, lithium-ion batteries. And what I want to talk about is a fairly general overview, which is, what are the applications? Where do we sit here in Australia in this industry? And part of the discussion might be that we have later on might be, well, where might we actually go? So, just looking at this slide, the current and future applications of batteries, I managed to find this particular slide, and I thought this is actually quite apt because we have road vehicles, large and small, there that increasingly are going to become electrified. And we already have, some of you in the room may already be drivers of electric vehicles. I think we're just simply going to see more and more and more, notwithstanding a whole bunch of other issues. People who live in apartments that want to charge them, there's a challenge. Large vehicles. There is a company outside Newcastle that is converting large trucks to large batteries. For example, you can see the houses behind, individual storage in homes. You can see the transmission lines large battery banks as we have in Victoria and around Australia, and of course globally. So that's all part of kind of today's world of batteries. Of course, we have them in consumer electronics. In the future, we're going to have them in trains. The big miners in Western Australia are already starting to say, let's convert our diesel-powered trains to electric trains. So that's a here and now. It's not on the rails yet, but they're very serious about doing it. We have things like flying helicopters there. This is a personal, basically a personal transport helicopter or gyrocopter, battery powered, for example. We talk about the hydrogen economy, and it's often talked about as a competitor to batteries. Well, actually, the hydrogen economy is going to need a whole lot of batteries to balance the renewable energy that's going to be used to produce the green hydrogen. If we want green hydrogen, we're going to need a lot of batteries to be able to balance that. So this is a market which is growing and growing in scale. If you look at here, the sort of the demand expected to grow about 25–27% annually. This is one forecast, but I looked across a number of forecasts. They're all in that sort of 25 plus or minus a bit compound annual growth rate for the business to around 4,700 gigawatt hours of production and even more deployment just by 2030. And you can see, this is where's the growth coming? Well, again, not surprisingly, that bar is China. We have Europe, United States, and the rest of the world. And somewhere in the rest of the world is Australia. Now, that means that perhaps we say, oh, we're a small market. But small is a relative thing when batteries are concerned. We're going to need gigawatt hours per annum if we're to meet some of the targets set by governments and aspired to by a lot of corporations in Australia. You can see the applications here, and what dominates is mobility. That's cars and trucks and trains and other forms of where you have mobility is the primary means or the primary application. It is the big market. We think about it often in terms of stationary storage to balance electricity in the grid or have a battery at home, but that pales in comparison to the mobility market. When you think that one Tesla Powerwall is about 13.5 kilowatt hours, and a Tesla or an IBM or a Hyundai or a Kia electric vehicle is 60 to 80 kilowatt hours of battery that you're driving around in. So it's cars are going to use 5 to 10 times more than any stationary storage application is ever going to use. And of course, you can see here, there's stationary and consumer electronics. That's where lithium ion started. That's the original Sony, and getting them into all sorts of portable equipment and then into laptops and then into iPads and iPhones and everything else. So that's where that all started. The value chain. Look at the value of the value chain here. Revenues, base case is 2030. This is billions of dollars per annum. Down here, it's even in 2022, it's still a pretty big market, dominated again by China as the manufacturer and the user, but it's growing, over 4 times in the space of 8 years. And that's not unfeasible. From all of the data that I keep on seeing and all of the announcements that are being made about manufacturing capacity and demand, that sort of growth is quite feasible. And again, you see where this is some of the supply chain, and I'll come back to this in a moment. The supply chain starts at mining. Australia is the biggest miner in the world, or is the biggest supplier of lithium, the raw lithium material. It has to be refined along with nickel and cobalt and iron and phosphorus and a whole lot of other materials, turned into active materials which make a battery cell, which are assembled into a pack, which ultimately gets, the pack is either the power wall or your battery pack in an EV as examples. And don't forget this one, reuse and recycle, and I'll come back to that. It's a big industry growing at a rapid rate, and it's not, this rate doesn't look like, have any indication that it's going to slow down. So you see, here, though, particularly in China, this is, and for me, who grew up in the photovoltaic industry, the solar cell industry, which is my original technical background and industry background, this looks all very familiar. There's a big market, potentially. A lot of investment goes into manufacturing. You get oversupply initially until the market stabilizes or the demand catches up. And then there'll be more investment in more supply and hopefully they'll gradually get into a better sync than what's happening at the moment. So at the moment, there's some oversupply of something up to 300 gigawatt hours of production capacity in 2023. And this is particularly in China. You see it here. This is the sort of supply base case. And so you're seeing demand, that's a sort of projected demand, and you're seeing this oversupply. And even back here, we're talking about pretty significant amounts of oversupply in manufacturing terms. That's good for consumers, or should be good for consumers, because prices should drop. Do they really drop? Sometimes I wonder at the actual buying end. So somebody's making some margin somewhere, but it's not at the manufacturing level, whether it's in China or anywhere else. This is being particularly driven out of China, this oversupply. So just to look at some statistics, the battery value chain here, we have mining, raw materials, all sorts of raw materials needed to make batteries, including copper, aluminium, there's vanadium for flow batteries, for example. And you see here the supply share of segment by country. Australia is the dominant at the raw materials and the raw, not materials, but the mining end here. But again, move across the refining to chemicals, the active materials, cell manufacturing. The dominant country is China. That's not a criticism. That is, China said, we are strategically want to be the world's leader in two particular industries. First one was solar cells manufacturing, where they absolutely dominate, and the second in batteries, and the third, I think they are really seeing is electric vehicles. So then you get to battery pack assembly, get a lot of it being done in Japan. But that will increasingly go to where closer to where the vehicle manufacturers are built. The European car manufacturers, are going to want their batteries and their battery packs to be relatively close to their assembly facilities. So they're not going to want to bring batteries by ship into Europe. They want them down the back, basically, just like they have their motors now. When you look at things like integration and maintenance, it's all local. That's just how that industry works. Reuse and recycling, again, that will be gradually moved from China dominating at the moment because it's the biggest user and the biggest manufacturer. We're all going to have to deal with reuse and recycling. And as an example of that, we have the European Batteries Alliance. This is their view of a circular battery economy. Again, going through raw materials active around the battery value chain. And these are some of the issues that we're all going to have to deal with, that governments and regulators are going to have to deal with. The inputs, technology, people. We often forget that there's not enough people to actually, or if you're going to have this massive scale up, where are the trained people going to come from? And they're going to come from universities, and it's a global market for people as well. It's not just a global market for technology, it's a global market for people and all these materials around here. Regulators are always going to get involved. Driving here tonight, I was listening to a program, and they were reporting on a lithium-ion battery fire, don't know what sort of battery, in Queensland, that's now killed the first 2 people from a lithium-ion battery, New South Wales, in Australia. And so it's, what do the first responders, how do they deal with it? And they're basically saying, we actually don't know, because when a lithium-ion battery goes off, good luck in putting it out. It's not easy. There's the value chain, the market, the business model, there's the supply chain, and of course, don't forget, societal and individual. We all make societal choices, governments often make those for us, but as individuals, this is a bit like solar. It's something that you can put and democratize just to yourself in your home. The one thing I would say that's missing here is that on this particular view is the fundamental need for capital to make it all happen. Without capital, none of this is going to happen. So the supply of capital, which some would say there's plenty of capital out there, that is relatively true, but making particularly for the newer generations of lithium-ion batteries technologies come along, we're going to have to keep on supplying capital to the entrepreneurs, the innovators, the universities, the government research agencies, to be able to keep developing and maturing those newer, higher density, different chemistry technologies that we're all going to need. So where is Australia in participating in the value chain? Pretty much more or less across most of it. We're not in EVs and we're not in consumer electronics. We are in energy storage at this end. So we've got multiple miners. They range from the small to the large, the very big. They range from BHP to small lithium miners. Lithium is the new sort of speculative stock. You know, just go and create register an NL company on the ASX, raise some money, and go and try and find some lithium. Except that market has fallen out at the moment. Chemicals and salts. So this sort of next level of refinement. There's interest. There is investment. There's been a push to establish, but we're seeing a pushback because as the price of lithium has dropped dramatically. That's really affected being able to do that part of the, get that interest going. There are some small and medium-sized companies operating in these active materials area. There's, for cell manufacturing, there's been announcements. Most of them have fallen by the wayside. I'd like to think ultimately we will get at least one decent-sized cell manufacturing facility in Australia. There are a few SMEs that import cells, put them into packs and put them into applications. There are multiple integrators. That's the integrators are the people who take the packs and put them into systems, usually for energy storage. And at this end, this recycling, reuse end, there are a couple doing it and a lot more thinking about it. And we're going to have to think about it because as the batteries in EVs age, there's by 2030, we're going to have a hell of a lot of gigawatt hours of old batteries something needs to be done with them. And again, the battery industry is just 10 years behind the solar cell industry, which has got exactly the same problem. So that's it from me. I think I would just emphasize that it's a very big industry. It's growing at a rapid rate. I can't see it stopping. There's a lot of new technologies that are going to continue to drive improvements. And I think we will hear some more about that from Amanda, but it's just an exciting industry to be in. I think from my point of view is how does Australia maximise its return from this industry to what we do here? How far up the value chain can we really go and still actually make a profit and make viable companies? Thank you.
Thank you, Bruce. So the plan of the evening is that we'll go straight on into the next speaker, and then we'll just open it up for general questions and discussions after Amanda. So let me introduce you to Amanda. So make my phone work. Professor Amanda Ellis is the head of the School of Chemical and Biomedical Engineering at University of Melbourne. And she's an expert on surface science and fundamentals of electrical and molecular interactions in a variety of applications, but in particular in energy storage, battery anodes, for example, and energy harvesting. She's currently working on research projects, including electrochemical testing of lithium-ion battery materials in standard cell formats, the superanode, and the National Battery Testing Centre. Amanda is board member and currently president-elect of the Royal Society, the Royal Australian Chemical Institute. So please welcome Amanda.
Thank you. Thank you for the invite while we're preparing my slides. I'm going to start right from the basics. So just what a lithium-ion battery is, and for many of the audience that might not know. So let's just start from the basics then. So the operation of a lithium-ion battery is really, we've got the cathode, we've got an anode. The cathode is usually made out of a lithium metal oxide in the case of lithium-ion batteries. For sodium-ion batteries, this is now, the state of the art is really Prussian white. Then we have the anode, which is usually in lithium-ion batteries, is graphite. And for sodium-ion batteries, it's hard carbon. So there are a lot of big differences between the two materials. We have the electrolyte that's in the middle here, and this just transports the lithium ions from one part to the next. And then we have a separator, which is very important because that stops material transfer between the anode and the cathode. And these separators are often different in lithium-ion batteries than they are in sodium-ion batteries. So you'll hear, I think at the moment, the state of the art is lithium-ion batteries. We'll be stuck with them for some time to come. Sodium-ion batteries, which I'll talk about later in the talk at sort of a long distance, maybe for more stationary storage, and etc. And you will also see at home, you've got what we call the coin cell batteries. So these are the lithium-ion batteries. You've got the cylindrical cells, you've got the prismatic cells, and then you've got pouch cells. And these are all for varying different types of energy storage around the world. Now, Tesla, which we hear a lot about, they use a cylindrical cell, so an 18650 cell, in a different and a focus mostly on nickel and cobalt in their batteries, but they've moved somewhat to lithium iron phosphate batteries as well. But BYD, which is beyond your dreams in China, they have now taken over the market. So they're the biggest manufacturer of electric vehicles batteries, and they use this technology called blade technology, which is really a somewhat sort of a flattened, I'm not really quite sure, it's obviously IP protected, but it's more around looking at a pouch-like or prismatic cell-like structure. And they've totally focused on LFP because LFP is a more safer version, and they're now getting a range of about 650 kilometers out of their batteries, which is an acceptable. I was thinking the other day, how often do I get into my car and think, well, if I'm going to fill it with petrol, how far can I go in it? But that's all we focus on with batteries, is how far can I go on it? And it's because of this fear of recharging. It's a societal thing, and as we evolve, we're going to get more opportunities to charge your car as you're going along the freeway and reduce that obsession with distance out of our batteries. What we want is really more rate performance. We want it to go when we want it to go real fast. Well, that's what I think. So the evolving market really, for lithium, this is in billions, so up to about 2032. We're looking at, significant evolving market. And I think, we've heard that from Bruce. When we look at the sodium market, it's not as strong, 4.8. Basically, it's going to be within maybe the next 1 or 2 years or 3 years, we're going to start to see sodium-ion batteries on the market. So it is evolving very, very fast. What they'll be used for will be another interesting discussion later on. So, and the reason really is because of the energy density. You just can't beat nickel cobalt in terms of energy density in batteries. Lithium iron phosphate, LFP, slightly lower energy density, but is safer. And that's why BYD is focused in that area, is around safety. And the sodium ion probably predicted in the next couple of years to get up to about 150 watt-hours per kilogram. Now, solid-state batteries, we hear a lot about those as well. They are totally an evolving market, and a lot of research is going into them, but we're talking about millions of dollars in the next 5 to 5 years. So it's not nearly the same market size that we're talking about with lithium-ion or even sodium-ion batteries. And probably with solid-state batteries, it's going to be more of a focus initially on conductive polymer electrolytes rather than anything else. That will probably be the first thing that hits the market. So what is a battery really made up of? So it's about 51%, or the cost is around 51%. It sort of correlates to what's in the battery. About 51% of the cathode. You've got the manufacturing, and then you've got the anode. Now, the anode is what I focus on, or we focus on with super anode batteries. So I'm going to probably do most of my pitch around the anode and the research around that. So the anode is as I said, in lithium-ion batteries is usually graphite. And graphite, you can have two types in the battery. So you've got the natural graphite, which is the mined graphite, and then you've also got synthetic graphite. And pretty much all synthetic graphite's made in China, and pretty much most of the graphite, natural graphite, comes from China. Now, this is a very highly energy intensive process. It can take, going up to 3,000 degrees Celsius. It can take about 3 hours to get up to that temperature. It takes about 14 days to cool back down again, and then you've got to start again. So it's a time-consuming, it's an energy-intensive process. And so in terms of the demand versus supply, what we're probably going to see is the demand for synthetic graphite is going to decrease slightly over the years, and we're going to see an increase in demand of natural graphite. And this is really based around our propensity towards a net zero and lowering our emissions. And mining natural graphite it produces lower emissions. So, as I said, most of the natural graphite comes from China. We're going to need about 2.9 megatons of graphite, and that's half, at least half of this is going to be natural graphite, if not more, in the future, to produce all these EVs and that are going to be around. So in Australia, we do have some companies that have started up with, they're not actually, a lot of graphite's used in lubricants and not necessarily in batteries, but once we start to see the possibilities of what we can do in Australia in terms of anodes, that will become more apparent. So in anode production, it's using natural graphite. You mine it, you crush it, you grind it, you do a flotation and concentration process. The two important processes here are spheronization. So you need to, I don't have time to go into any detail there, but you need to make spheroids of the graphite. So it's got a lot of edge planes so that the lithium can impregnate between the layers. There is a great deal of waste from this process. So about 60% of waste graphite produced in terms of fines. And we're looking at applications to use those fines for high-speed applications. So this is where you really want to do rapid charging very quickly, because your particle size is very small relative to about 12 microns that you need for these spheronized particles. Then you do some chemical purification. In China, it's HF purification, which anybody knows, anybody that's even not a chemist knows that HF is bad. If you've ever watched, what is it, Making Bad or whatever it is, Breaking Bad, you don't use HF. And so there's companies like Ecograph that's out of Western Australia that's looking at more of an economic, an environmentally friendly way of doing purification, which doesn't use HF. And so there's a big market open up in research and potential there to move away from that. Now, I would argue the most important thing in a battery is the carbon coating that goes on the graphite anode. It is the most important thing. It stabilizes the battery. It stops the battery, the anode, from falling apart. And this is a carbon coating, and it's a nano layer of carbon coating that's put on the anode material. People like Ecograph and many other companies are looking at alumina coatings. This stabilizes what they call the solid electrolyte interface. So this means that you get really good charging and discharging out of the battery, and it doesn't fall apart. So this layer here is really important, and it's important economically because it moves this material from $3,000 US per ton up to $12,000 to $15,000 US per ton. And all of that is done in China. Every single person that mines graphite, spheronizes it, sends it to China for carbon coating, and then it comes back again for battery assembly or whatever. So it's really something I would argue that we should think about doing in Australia, but doing it, research is showing now how to create this beautiful carbon layer at much lower temperatures using materials that are available naturally in Australia, and so forth. Now, the issue with graphite is that it doesn't have a very high capacity for lithium. It's down here in this region. Oh, sorry, the axes haven't come through. It's about 372 million hours per gram. And then what a lot of the markets are looking at is introducing silicon into the anode. Around about 10% silicon goes into the anode because the silicon has a very high specific capacity. And so if we introduce that in there, we can get up to about 1,000 milliamp hours per gram from our anode, which means then we can have lighter weight batteries. We don't need as much material in our batteries for the matching cathode. But the big problem with this is that the exfoliation of the pulverization of the material. As you put lithium in, take it out, put it in, put it out, it breaks up the silicon into tiny pieces. So there's a lot of research or new research going into different ways of mechanical milling, using vapor deposition of carbon coatings on this material to try and improve the performance. So what we're looking at in terms of the timeline, so we all started off with a trusty lead acid battery. We moved quickly into these nickel batteries. A lot of them, you'll recognize the lithium alkali batteries. These are cheap and cheerful, don't last very long. These are the ones that we really have enormous volumes of to recycle, and not really much added value in them really, but we've got a lot of them. And then we've also, and of course now we've got the nickel, cobalt, manganese, or nickel, cobalt, aluminium, but all these different types of batteries. The one that really is on the market, has that everybody's working towards now, is the 811, NCM 811. And this is because we want to get higher nickel concentrations into the batteries. We're using less cobalt, so it makes it cheaper to make. And there's also talk about the NCM 900. You can work out what the zeros are. But there's a lot of work going on in there. And so once we move past that and we get into the post-lithium era, then we're talking more about using things like lithium sulfur batteries. Now you're talking about having a lithium anode, or you're talking about silicon anode. So now you're talking about changing the anode. You don't need the graphite anymore. So there's a lot of research around that. There's the aluminium air, magnesium air, but lots of different types of air batteries. And then this could be lots of debate and argument around this, but sodium ion batteries are in the foreseeable future are going to be a long way coming. Now, in terms of energy consumption, where we're moving in the future is, so up the first up to, I think it's, sorry, this has not come out very well, up to the brown is all, before that is all lithium ion, and up after that is all of these new post-lithium ion batteries where we won't need this anode, necessarily this graphite anode. And so there's a lot of saving and energy savings in doing that as we move forward into these post-lithium batteries. But nonetheless, you're still going to have things like coating and drying are the most energy intensive, so making the electrodes for the batteries. There's a big push to make dry electrodes. So there's a lot of research going into using dry electrodes, because to make these electrodes, you use quite nasty solvents like NMP and things like that. And they all get into the environment. So there's the coating and drying, there's the conditioning, which we can't really get away from. This is the charging of the battery. Every single battery has to be charged to start with. And so there's the electricity that's required for that. We need to focus on renewables for doing that charging. We can't use fossil fuels or coal to charge batteries. It's just not what we should be doing. And the other thing is dry rooms. So when we're looking at lithium or nickel, there are explosive materials. The electrolytes are at the moment are solvent-based materials. These needs to be done in a dry room. And so there's a huge energy cost. If you're looking at manufacturing and huge factories out in the outback, you know, where are you going to get the energy to pump, you know, to keep dry rooms? So lastly, I'll finish off with recycling, because I think that is really something that we can all agree on is a necessity. I think the biggest thing I have is, what are we going to do with the stuff we've recycled? You know, so we talk about not manufacturing batteries. So what are we going to do? We're just going to bring them into Australia. We're going to recycle them, and then we're going to send the product back again. And we have a habit of just sending stuff to other places and not getting the value add that we should be as an advanced technological age. We're looking at, you know, the Accord is saying 80% of our people should be tertiary educated. You know, what are we going to get them to do? Right? So battery recycling is mostly in China. It's around pyrometallurgy, again, an energy intensive process. And so the Europeans are doing more hydrometallurgy, and that's their big push. And same with the United States. They're sort of trying to plan or match what their consumption is. So I don't know, there's no growth in here. And I just had in this, my last little bit here is just for the nerdy chemical engineers amongst us. This is a flow diagram about current, just one example of how a battery is recycled. And the important part here really is, or the dangerous part is really in this case perforation and shredding, and getting an understanding of how we do that is also equally as important as how we actually extract the minerals, because safety is absolutely paramount in anything we do. Okay. Thank you very much.
All right, Amanda, if you could just stay there, that was great, thank you. Just stay there with Bruce. Okay, Sandra's going to on the mic, and then the floor is open. So thoughts, questions, comments, please. Oh, I'm sorry, just hold on for the mic. So, go on. Yeah.
Well, except I can't turn it on.
And then I think what we're going to have to do probably is have you come here.
No battery.
All right. So what? No, that's all right. Yes. Oh.
Yeah.
Magic. I guess I wanted to know, from being in India last year, there was a lot of discussion around the usage of batteries in India, the recycling of batteries. I mean, where does India fit into all of this in terms of both manufacturing and as an end user?
So I'll have a first go. India is, sort of many years behind China, but it's got the same problems that China had 20 years ago. Yeah, the fascinating thing to go to India is it's a bit like all of Asia and Southeast Asia, it's to avoid being run over by scooters and tuk-tuks, and that's where the first big markets, doesn't matter whether you're Indonesia, anywhere in South Asia, Southeast Asia, that market is going to be massive and is really being looked at by some of the big scooter and motorbike manufacturers right across that whole region, and there's indigenous ones in India. Of course, India's got it's still got to electrify a lot of people in a stable, continuous. Yes, I can turn on the light still, or yes, the refrigerator will keep going. So there's that sort of. It's a big market which is going to keep on growing and needs to do that. For both mobility and stationary. The Indian government has already said we want to be a manufacturer. We want to be a global manufacturer, not just to supply our own. So they want to try to replicate China to some degree, or to a pretty high degree. You've got companies like Reliance and Tata are really getting into that now, and there'll be other startups. Of course, there's lots of there's lots of researchers who are very, very good researchers who know quite a bit about batteries and lots of other things in India. So there's an ecosystem there. It's about how does that all come together and how is it going to be? So there's a market. There are people who are interested in being local suppliers and local developers, technology suppliers. The question, again, I think for countries like Australia is how do we work with a country like India to help them achieve what they need to achieve and what they want to achieve.
I wonder if Amanda's got any thoughts about where India might fit into the recycling on all of this, because currently India does recycle a lot more materials than, for example, we do.
Well, that's true, but not batteries. I actually just wanted to come back to more about the safety issue and the production of batteries and the safety around mining and in India and where we can help support them in their growth around developing the knowledge that we're going to create in Australia, hopefully through the mining and potentially the manufacturing of batteries. So I think it's the biggest concern I would say for India is around the safety. I hear of companies that wanting to do the spheronization of the graphite, and it's not done in a way that's sustainable for a start, and it's also not done safely. So I think that's sorry.
It's the same in China. It's not done in a sustainable way in
Yeah.
countries, and that's the other side of the energy and the environment marks that go into these things.
I think, you could argue China's a little bit more advanced, and I think that they do have, a degree of understanding of safety but I think India needs sort of to be educated in that space and supported, because we're going to have to support. I mean, I think we would all agree that we live in a balloon, and if we're not supporting other countries, and it's particularly other countries that are going to develop and should develop, we need to support them through proper, sustainable practices and show them how to build factories that work properly and can, lower emissions and that sort of thing. I think we have a responsibility. Yeah, sorry, that wasn't your question.
No, that's okay. That's okay. Other questions, comments? Leonie.
I had a question that's around designing for recycling. So I guess within a supplier like Tesla, can they switch out different battery types within a vehicle? Are they designed to be able to do that? So as the technology improves, they can take out the lithium ion or whatever battery and replace it. And then the next stage would be, can you do that cross suppliers so that you're actually helping design for recycling and design for, you know, upscaling your technology. Do you see any signs of that, or is it way too early?
Well, I think if you see, you know, like BYD, for example, I mean, they're very, that's sort of their market pitch, and that's what they're trying to grow in that area. And so the design of, you know, the blade battery and everything is very unique to them. Elon Musk thought it was hilarious, and it's turned out to be an amazing success story. Now they're the market leaders. So I think, yeah, in terms of recycling, there is definitely an idea. How are you going to do that? Because, you know, it's the electrolyte that's the problem. So if we can design better electrolytes, and we know that, you know, Deakin University is really on top of all of that with Maria Forsyth. So if we can design better electrolytes that we can momentarily pull a battery apart and put it back together again, you know, get rid of the anode or regenerate the, whatever we need to do. I think there's options there, but until we get, you know, more stable electrolytes, it's going to be a challenge. But you can design a vehicle so that you could maybe have cylindrical cells at the moment, but then put in the blades later. I mean, that's a vehicle design.
Yeah, David, well, I'm just wondering what the latest thinking is on the cost of the levelised cost of electricity from batteries for firming purposes, because about 5 years ago, a college did a study which was largely led by our academy, looking at the cost of electricity from pumped hydro energy storage, and it touched on batteries. And at that stage, if I recall correctly, we were talking about the levelised cost of electricity. If you've got to consider all of the capital cost and the cost of capital of the operating and so on, for pumped hydro storage, it was about $200 to $500 a megawatt hour. And I suspect it's a hell of a lot more from snowy hydro too. Batteries were $200 to $300 a megawatt hour, something like that. I was just wondering if there's been any recent thinking about or estimates of what the cost is likely to be, considering, you know, the need for firming power.
Good question, David, to which I can't give you a direct answer because I don't think I certainly don't know. Again, storage for electricity is something that you need, as you well know, and many in the room will well know, you need it from milliseconds to sort of months. And so it's different. So from my point of view, you're looking at different applications for batteries versus pumped hydro, etc. And things like flywheels, you know, really short, etc. So the only thing I can say to you is that the costs are continuing to drop. So the LCOE is going to continue to go down. How competitive it is today. So if you put, you know, 8 hours of battery storage, which is kind of a hell of a lot, to be honest, today, if you put 8 hours of battery storage with a 250 megawatt wind farm, it's probably levelised cost of energy is probably relatively high. It'd be mostly dominated by financing cost, frankly. The rest, you know, how would that compare to a 250 megawatt small nuclear reactor, modular reactor, or against a new gigawatt coal-fired power station? I don't know the answer. Their CSIRO sort of does its projections. They're either believed or not believed, but they're probably the best that we've got in Australia. So it's a very good question to which it's a variable answer, and I don't have the data to be able to give you. But it is going. All I can say is, again, just emphasise that costs are coming down of batteries, and I think their lives will continue to get longer and longer.
Yeah, I do my own back of the envelope estimates based on the cost of capital and the published data for various energy or battery projects around Australia. And you're talking about well over 100, possibly $200 a megawatt hour.
Yep.
But putting that aside, that's not unreasonable if we're getting sort of $20 or $30 or $50 a megawatt hour for renewables
Correct.
during the day.
Correct.
But the interesting thing is that if you look at the period July, August, September, particularly July and August, you often get 6-week periods where there's very little sun,
Yep.
and very little wind.
Yep.
And I recall 2 years ago, I think it was, that the during the shoulder periods, power was normally several $100s a megawatt hour for hours on end
Yep.
on the spot market. So that makes batteries viable then, but for the rest of the time it may not be. So I think it's a really important issue. I think there's lots of statements about the prices coming down, but really how much will they come down is what I'd like to know.
In terms of it's in terms of capex, we've seen it. So where we've really seen the drops in capex are in vehicles. You know, the battery packs in vehicles were, even a few years ago, hundreds of dollars a kilowatt hour. They're now down to the battery pack, so the pack that goes in is now approaching, you know, sort of less than, probably about $120 a kilowatt hour, and they've got all the goals to get it way less than $100 a kilowatt hour, and they'll do that through the usual economics of manufacturing, which is scale manufacturing, where you put in better technology that increases capacity, plus you just make gigawatt hours more and more of them. So it's learning by doing and learning by technology. So I believe we'll see that continuing to drop. I think in terms of the applications, the LCOEs, that issue of what happens in wintertime, etc., that for me all then points to, well, what are we going to do about transmission? Because we've got to interconnect more of the country to be able to take advantage of what's happening in Queensland, in Victoria, in the middle of winter. Now, that adds another dimension of cost to LCO, delivered LCOE. It's not so much LCO production, it's about the delivered cost. So your TUOS is going to go up a lot more, even though your DUOS and production costs might actually, well, production costs will drop, DUOS will just stay the same. But unless we interconnect, we can't get the benefits of living in a big country. And it's the same in the US.
Bruce, Australia has a lot of the resources required to manufacture batteries.
Yep.
And from your perspective, which part of that cycle should Australia be involved in?
I would like to see Australia involved in every part of the cycle. At the cell and pack level, that should be for stationary storage, because we're not an EV manufacturer. And why would Volkswagen want to buy battery packs and put them on a boat and send them to you know, outside Munich or wherever they are? So I would like to think that we will move further up that value chain from being a raw miner. I also do not underestimate the difficulty of doing that and the cost, and we're seeing it now. There were a lot of announced projects in Western Australia, for example, about, yes, we're going to do lithium hydroxide or lithium carbonate, and they're all being put on ice because the cost of lithium dropped so much that they were unviable in the Australian context. Actually, they're probably unviable even in the Chinese context, but the Chinese will wear it for a long time. So I'd like to think that we will go down that path. I'd like to think that we will have at least one decent size gigawatt, you know, sort of multi-gigawatt hour cell manufacturing facility in Australia. I don't care whether it's lithium or it might ultimately be sodium. It doesn't matter, but it should be focused to our local market needs and our regional market needs and be a supplier into that. And we're going up against all the countries that want to do the same thing, not just China. I've just come back from spending some time in Vietnam on holiday. Vietnam wants to be in that world as well.
Indonesia has to stay in the middle industry.
Yep. That's right.
Any other questions? Comments? Sorry, Dan?
I will take a question in terms of recycling of batteries, particularly the graphite. And I'm just curious, how, the graphite is recycled. And can graphite be recycled to reuse in the display battery or for other applications?
Okay, no, that's a great question, and I'm obviously a bit of a sort of an emerging passion of mine. Look, the binder is a big problem. The binder of the anodes is a huge problem. And anodes, it's PVDF often, so it's a fluoropolymer. It's really hard to get out. It's hard to get, once it binds with graphite, it's really hard to remove. But we're moving, say, for example, in the silicon graphite anodes, we're moving more to polyacrylamide, PAA, polyacrylamide. So we're moving more into those sort of soluble based polymers. So the binding for recycling is really important. So hopefully as batteries evolve and we start to get better performance with different types of anode structures and different types of anodes, we'll be modifying those binders. Now then the secondary problem, once we've done that, is you have to have them spheronized. So through the recycling, it has to remain spheronized, and more importantly, it has to remain with the carbon coating on it, because that is the be on or end all of the anode. So you could argue you could recycle it, get the spheroids out, and then do the carbon coating. But either way, all you're going to end up with is just a load of useless graphite. So I think there's a lot of research to delicately recycle or separate out the graphite. It's not as simple as I think people think, and it's certainly not worthless. If you can recycle it with the carbon coating, then you've got a product. As I said at the beginning, though, is why are we recycling? I mean, we're recycling it because it's the right thing to do. But what are we going to do with all the materials that we're creating from the recycling if we're not going to manufacture, or we're not going to go back to creating our own batteries? Now, I would argue that stationary storage is important, and it's sort of the crux of the matter. But I also think we have to think beyond where we are now, when these batteries are really going into, we work out the transportation of microgrids and all of those sorts of things. We might be living in a different world than we are currently living now. So sovereignty is going to be important again. We saw that with, we don't want to hark back to, COVID, but it was a real issue for the planet. And so we might go back at defence. What if we can't have batteries? What if we can't put them into our submarines, or we can't, we've got to import batteries in for some of our defence operations. I know it's a bit negative, it's a catastrophic kind of way of thinking, but I do think that we have to somehow think a little bit about retaining some of the technology and the production and manufacturing of such an important thing as energy, and how we store it and how we use it. So, yeah.
Very good. Thank you, Amanda, for those. Thank you, Amanda, for those sort of big picture comments right there. That, I think, just about uses up our time. Kitchen gets grumpy if we're not out there by 7:30. So first of all, thank you to both Bruce and Amanda from behalf of all of us for stimulating a very interesting, and of course will continue to get more and more important to us all in the future discussions. So can we thank them both again? And then I think Sandra would like to have last word.
I need to thank Doug as well for excellently chairing today's session. So we give Doug a round of applause as well. Feel free to continue the discussion over dinner for those of us staying for dinner, because I think there are lots of questions. Otherwise, if I can just briefly advertise our April event, which will be a week later than normal, it'll because of Easter, so it'll be on the Tuesday the 9th of April. Complete change in topic. We will be talking about microplastics and other emerging contaminants. And we have lined up two excellent speakers, Andy Ball and Mina Saristo, speaking to us on that topic in April. So thank you.